Okay, so today we are going to talk about chapter 5, which is relatively easier than the previous two chapters. So let's see what we are going to do. So in chapter 4, we studied how to analyze thermodynamic devices such as nozzle, diffuser, turbine, compressor, and heat exchanger, etc. So in this chapter, we are going to combine these thermodynamic devices to make a cycle. So we are going to study 3 cycles, and each cycle consists of several thermodynamic devices. Okay, so we are going to study 3 thermodynamic cycles. They are heat engine, refrigeration, and heat pump. So we are going to study how to evaluate these thermodynamic cycles. Okay, so to study these thermodynamic cycles, we need to understand what is thermal energy reservoirs. So we are going to study what is thermal energy reservoir. It's a hypothetical body with a relatively large thermal energy capacity. That means the amount of these thermal energy reservoirs are abundant. Therefore, even though there is a heat transfer, the temperatures, the properties of these thermal energy reservoirs do not change. So what does it mean? Think about this way. If you go to the, the east from Mount Pleasant, not east, let's go to the west, because I don't remember the name of the lake this side. So if you go to the west, you see the Lake of Michigan, right? So let's assume that the Lake of Michigan is at 20 degrees Celsius at this time. So now you are going to buy a hot coffee, let's say 100 degrees Celsius. So if you pour this coffee into the Lake of Michigan, do you think that the temperature of the Lake of Michigan goes up because you are pouring hot coffee? Not really. Why is that? Because the amount of water in the lake is a lot. So even even we pour hot coffee, it doesn't change the properties of properties of Michigan Lake. The same thing. Thermal energy reservoirs, we assume that the amount of each reservoir is a lot. Therefore, even though there is a heat transfer from this or to this, it won't change the temperature of this body, that is thermal energy reservoir. Then why do we use these concepts? Let's talk about how we produce electricity. We produce electricity by using a thermodynamic cycle. So briefly speaking, we use a steam generator. Which will generate steam by heating water. So to run this steam generator, we need to provide heat. So how can we provide this heat? How do we produce this heat? We can produce this heat by burning fossil fuel, or having nuclear reaction, or concentrating the sunlight, or collecting the heat from underground. So by using this heat at high temperature, we can boil water that will generate steam. And this steam is going to enter a turbine and expand in the turbine. Due to the expansion of this steam, we can produce mechanical work, that is turbine work. And at the exit of this turbine, we have leftover steam is going to be released. So we have a condenser where we can reject any waste heat. So in this condenser, we use a coolant from, let's say, nearby lake or nearby river or ocean. So we can use those coolants to remove heat from the steam. So we reject heat Q out. And then we need to, return this steam back to the steam generator so that, it can be a cycle that is pumped. So this becomes a thermodynamic cycle. So we can produce mechanical work. That mechanical work is going to run generator to produce electricity. So this is what happens in most power plants. And that's how we produce electricity, so we can study in this room, right? This cycle is called Rankine cycle. And that we are going to study later in chapter 8. And this is one example of heat engine. So in a heat engine, we observe heat from high temperature, produce work, and reject waste heat. That's what happens in a heat engine. And this Rankine cycle is just one example of this. Okay? Then, to produce electricity, what we need to do is, what about if we don't have enough fuel to produce heat? Maybe at the beginning, the temperature of the heat is going to be 500 degrees Celsius, which is high enough to produce steam. What about if we don't have enough fuel? The temperature of the source is going to, decrease from 500 to 400, 300, and at some point, this power plant is going to be, the stop, right? So to have a steady state operation, we need to provide heat at a constant temperature. That is the concept thermal energy reservoir. So we assume that the amount of fuel is unlimited. Therefore, we can provide heat at a constant temperature, regardless of how much electricity we produces. We assume that we have a plenty of fuel, so we can burn and produce heat at the same temperature, 500 degrees Celsius. What about in the cooling side? We need to reject heat at steady state. That means that the coolant which is going to be used in this condenser should be at a constant temperature. So let's say, that we are using water from nearby river. So let's say Chippewa River, and then we use the water from Chippewa River, which is at 20 degrees Celsius. So if in a normal steady state operation, we assume that the amount of water in the river is plenty enough. So even though we continuously produce electricity, the inlet of the coolant system is going to be at 20 degrees Celsius. But what if the river is dried out? Then the temperature of the river is going to increase, and the temperature of the condenser is going to increase from 20, 30, 40, 50, and eventually the power plant stops, right? So to have a steady state operation, our assumption is the temperature of the source of the energy, the source of the heat, the temperature of the sink of this heat should be at a constant temperature, 500 20 degrees Celsius, no matter what happens. So this one maintained at 500 degrees Celsius. That is high temperature thermal energy reservoir. This one maintained at 20 degrees Celsius is low temperature thermal energy reservoir. To run this cycle continuously, we need two thermal energy reservoirs. One is at high temperature, the other is at low temperature. Okay? That is what is written here. So thermal energy reservoirs, we have a source of thermal energy, we have a sink of thermal energy. We assume that the amount of this source and the sink is a lot, therefore their temperatures do not change. So that we can have a continuous power production. Okay? So that is our assumption to study chapter 5. And this is what this is what is reality. We produce electricity 24/7. That means that we continuously provide fuel to a power plant that supply electricity to campus. So the source of that heat is going to be always at a constant temperature. So that is thermal energy reservoir. And regardless of what substance that we use for coolant, can be air cooling or water cooling from a river or lake, we assume that the material, the coolant is plenty enough, so their temperature, its temperature remains constant. So we have two thermal energy reservoirs to produce electricity to turn on the light here. Okay, so that is our the assumption. Then let's study the first cycle, which is heat engine. Heat engine is a device to produce work. So let's see, to run a heat engine. By the way, this is one of the examples. To run a heat engine, this example is called the Rankine cycle. This is heat engine. So to run this heat engine, how many thermal energy reservoirs do we need? We need two. One at high temperature, and the other at low temperature. And no, it doesn't need to be a specific temperature, as long as the temperature remains constant. Okay? So, in a certain power plant, the temperature of, the high temperature thermal energy reservoir is going to be 500, or another, the heat engine can be, the 600, and the other is going to be 400. It depends on, how you design that specific power plant. Okay? So we have two thermal energy reservoirs. One is at high temperature, TH, and the other one is at low temperature, TF. And but the difference between the thermal energy between the source and the sink is going to be what? The net work that we produce. So that is a heat engine. So when you have a heat engine, how many thermal energy reservoirs? One at high temperature, the other at low temperature. The difference is going to be the net work that we produce. So if we rewrite this one in a simplest, the form, we have a heat engine. It has two thermal energy reservoirs. One is at high temperature, TH. The other one is at low temperature, TF. And the heat transfer direction is from high temperature to heat engine, from heat engine to low temperature. High temperature to heat engine for the amount of QH. From heat engine to low temperature for the amount of QF. And this heat engine produces net work, W net. So this is what heat engine looks like. Okay? Then how can we analyze? Okay, so I see, what heat engine looks like. How can we analyze this heat engine? We can first think about energy balance equation. Since it is a steady state, let's use a rate form. What is the rate form? We divide each term by time. So instead of Q, instead of heat transfer, we can say the rate of heat transfer from this high temperature thermal energy reservoir, Q dot H. Instead of QL, the rate of heat transfer, the rejected from heat engine to a low temperature thermal energy reservoir, Q dot L, and we can produce net power, which is W dot net. Then, can we apply energy balance equation? Yes, we can. And how? The energy balance equation for steady state open system, we studied that it is E that goes into a control volume should be the same as E dot leaving the control volume. So it means that the sum of any energy transfer into a control volume should be the same as the sum of any energy transfer leaving that control volume, so that it can be a steady state operation, right? So what kind of energy transfer in? To determine whether energy transfer is in or out, you can just look at the arrow. So how many goes into this heat engine? There's only one arrow goes into this heat engine. That is Q dot H. So we have Q dot H that goes in. Anything else? No, that's it. What about Q dot L? Is energy transfer leaving heat engine. W dot net is also energy transfer leaving the heat engine. So Q dot H is going to be Q dot L plus W dot net. If we rewrite this one in terms of W dot net, the net power that is produced by this heat engine is going to be the difference in the rate of heat transfer between the high temperature thermal energy reservoir and low temperature thermal energy reservoir. So this is the energy balance equation. Okay, that was simple. Then how can we evaluate the performance of this heat engine? Is it working good or not? Is it a good heat engine or a bad heat engine? How are we going to evaluate that? By using efficiency. You remember from chapter 2, we studied efficiency. Efficiency means desired output over required input. Then what is desired output? Why do we, run a heat engine? To observe heat? To reject heat? No, we want to produce work. So W net is going to be, W dot net is going to be desired output. Then to run a power plant, what is required? We need to produce high temperature heat so that we can produce steam that will run turbine, right? So what is required input? Q dot H. So we need to have heat transfer from the source of thermal energy to the heat engine. Q dot H is the required input. That's how we determine the efficiency of this heat engine. Then, according to this energy balance equation, W dot net is the same as Q dot H minus Q dot L. So we can rewrite this efficiency in this way. Q dot H minus Q dot L over Q dot H. Then Q dot H over Q dot H is going to be 1. It's going to be 1 minus Q dot L over Q dot H. So these are how we determine the performance of this heat engine. In other words, efficiency. So that's everything about heat engine. Pretty simple compared to what we did in the previous 2 chapters. So let's solve problems together. A couple of problems. The first one is there is a heat engine. It pumps water out of an underground mine. What is a heat engine that pumps water from an underground mine? It's called geothermal power plant. What is geothermal power plant? We, the pump water underground, and heat from underground is going to produce steam. So when we pump water underground and steam comes out, that steam is going to run turbine and condenser and pump, etc. So that's how we produce, that's how we run our power plant. That is geothermal power plant. Then how can we analyze it? It's simple. Using this energy balance equation, by using this efficiency. So let's do that. So we have a heat engine whose energy balance equation is W dot net is Q dot H minus Q dot L, and the efficiency of this heat engine is going to be W dot net over Q dot H, and can be rewritten as 1 minus Q dot L over Q dot H. So we have these 2 governing equations. Which one? This one? Greek letter ieta. Ieta or something. I don't know. I'm not from Greece. Anybody from Greece? I heard that it's ieta or something, right? No? Nobody from Greece? Okay. Ask ChatGPT. You can just say efficiency. That's the name in English. Okay, so let's solve this problem. So this heat engine accepts 700 kilojoule. That is the heat transfer from the source. So this is the heat transfer from the source. 700 kilojoule. How much work does it produce? 250 kilojoule of work can be produced by this heat engine. So the net work produced is going to be 250 kilojoule. Then how much heat does it reject? 700 minus 250 is going to be 450 kilojoule. So this is the heat transfer to the cooling system in the condenser. That's it. Is it hard? Not really. It could be, right? Okay, so we have another problem that uses the same governing equations. So let's see. We have an automobile engine that produces work. So it is also a type of heat engine. Anything that produces work from heat can be called heat engine. So let's analyze this automobile engine. So it's a heat engine. So in a heat engine, we have two thermal energy reservoirs. One is at high temperature TH, the other one is at low temperature TL. And the direction of heat transfer is going to be from high temperature to heat engine, from heat engine to low temperature, for the amount of QH and QL. And by doing so, we can produce work, that is net work, W net. So this is heat engine. Then, based on that, we can come up with two governing equations. The first one is this energy balance equation. W dot net is Q dot H minus Q dot L. And the efficiency is going to be W dot net over Q dot H. By the way, as you can see, we are using kilowatt power, not work. So we can add that on top of it to show that this is rate form. So that's the starting point, okay? So let's solve this problem. It delivers 55 kilowatts. That means this one is 55 kilowatt. Okay, good. If the fuel has a heating value, okay, 44,000 kilojoule per kilogram, that means if you burn 1 kilogram of fuel, it's going to produce 44,000 kilojoule of heat. And the density of this fuel is 0.8 gram per centimeter cube. Determine the efficiency of this engine. Then one thing you can notice is that liter per hour, gram per centimeter cube. Why the units are so ugly? Because the actual problem is pretty simple. So let's see. Determine the efficiency. Where is the efficiency? This one. So we want to determine this efficiency. That means that we need to know the net power and the rate of heat transfer from the source, which is the fuel. And we already know the net power. The net power is 55 kilowatt. So if you can determine the rate of heat transfer from the burning of fossil fuel, you can determine Q dot H. Pretty simple. Then how do you determine Q dot H? It's simple. Mass flow rate times its enthalpy. Then what is the mass flow rate? And now what is the enthalpy? The heating value. So this one is the heating value, 44,000 kilojoule per kilogram. So if you know the mass flow rate, you can determine Q dot H and problem solved, right? So let's see how we can determine M dot. There are two different ways to determine M dot. The first one is density times average velocity times cross-sectional area. Do we know any of them? Not really. Then what is the other way to determine the efficiency? Density times volumetric flow rate. Do we know the density? Yes, 0.8. Do we know the volumetric flow rate? Yes, 22. The problem solved. But there's one thing, which is the unit. So as long as you know how to do, the unit conversion, you can solve this problem. No worry. So let's do that. What is the density? 0.8. What is the unit? Gram per centimeter cube. What is the volumetric flow rate? 22 liters per hour. Now you can feel pity on whoever developed this problem because he did so ugly job to make it complicated. But we know how to do unit conversion, right? So the unit that we want is going to be kilogram and second. So let's, evaluate one by one. Now there's a gram. 1,000 gram is 1 kilogram. So if you want to, remove this gram, we're going to put this gram in the denominator. 1,000 gram is what? 1 kilogram. Then we have a centimeter cube. We don't like centimeters. We like meters. So 100 centimeters, one meter is 100 centimeters. So how can you convert? Centimeter is in the denominator, so centimeter should be on top, on the numerator. Centimeter. 100 centimeter is 1 meter. Oh, wait, it's a centimeter cube. Okay, no problem. Centimeter cube. Then we have a liter. 1,000 liter is 1 cubic meters. So we want to get rid of this liter. Liter is in the numerator. So I'm going to put 1,000 liter in the denominator. So 1,000 liter is what? 1 square meter, 1 cubic meter. An hour. 1 hour is 3,600. 1 hour is 3,600 seconds. And let's see. Gram, centimeter cube, make sure that this is 100 cube, and meter cube, liter, hour. So what is the unit? Kilogram per second. Then this m dot goes in here. Then that will be q dot h. If you do the calculation, you get q dot h. That is 215. 215.1 kilowatt. So now, can you determine the efficiency? Yes, you can. So what is the efficiency? 0.256. In other words, 25.6%. This is the efficiency. Any question? There's nothing wrong between, there's nothing difference between here and there. It just has more unit conversion. Yes, your question?
Sure. That H is
Mass flow rate times the heating value. So the previous one was simple. This one, we are using the same governing equation. Should be simple. As long as you know how to do unit conversion. So if I give you this problem in your second exam, can you solve it? Yes, you can. So that's everything about heat engine. Any question? Yeah, these are heat engine. That was the first cycle shown in this chapter. By the way, there are 3 of them: heat engine cycle, refrigeration cycle, and heat pump cycle. We just finished one of them. Is it hard? Not really. The governing equation is pretty simple. We learned how to make the energy balance equation. We learned how to, determine its efficiency. That's all. Huh? That's in class? What do you mean that's in class? That's all. That's all. 4 heat engine. That's all 4 heat engine. Then we are going to talk about 2 more cycles. But don't worry. Refrigerant cycle, there's a good news. There's a good news, okay? Refrigerant cycle, heat pump cycle, they are identical. They are the same. They have the same technology. We are just use it differently, okay? So the following, the next cycle is going to be just 1. And we are going to use that 1 cycle for 2 different applications. One is refrigeration cycle, the other one is heat engine, okay? So let's talk about that. We know what is a refrigeration cycle from our experience. You all have a refrigerator. You don't? You should, right? Unless you live in maybe Iceland or something, right? You have a refrigerator, right? So you know how it works. We maintain food at low temperature. That's what a refrigeration system is about. So let's talk about that. So this is a refrigerator. There's a food inside. What kind of food? Milk. Okay. That isn't it drink, not food? Okay. So there's a milk, and what else? And there is apple. Do we put apple in the refrigerator? Or outside? What do you mean? Okay. Then leftover steak from yesterday's steakhouse. Totally burnt steak. Okay. Okay. So what this refrigerator is about? So what happens thermodynamically if we don't do anything? The inside is initially at low temperature, 3 degrees Celsius, and outside is what? Usually we put a refrigerator in a kitchen, so outside is going to be the air in the kitchen at 20 degrees Celsius. So tell me what's going to happen. Naturally, there is a heat transfer. From where? From 20 to where? 3. According to the second law of thermodynamics, heat transfers from high temperature to low temperature, which is, the pretty easy to understand. So because of that, what happens? The temperature of the air in the refrigerator goes up. That's what happens when you have a power cut, and the first thing that you worry is going to be whatever inside your refrigerator, right? Because its temperature goes up. Because of the famous thermodynamics law, the second one, heat transfers from 20 degrees Celsius to 3 degrees Celsius. To avoid that, what we need to do? We need to have a heat transfer, the exact amount of heat transfer to the other side. So let's say there is a natural heat transfer from kitchen air to inside, let's say 20 watts. Then how much heat transfer we need to make artificially? 20 watts. If we make 30 watts, what happens? This 3 degrees Celsius goes down. If we make 10 watts, temperature goes up. So if we make exact 20 watts, matching each other, then we call it thermal equilibrium. The temperature remains constant. So what we want is that we want to transfer heat from inside to the outside. Then tell me, is it possible? No, because of the second law of thermodynamics, you cannot transfer heat from 3 to 20. Then what do? We use a refrigeration cycle. Then let's talk about refrigeration cycle. We usually start with a compressor. So there's a compressor, usually located at the bottom of your refrigerator. Looks like this. And to run this compressor, what we need to provide? We need to provide work, W net. Let's assume that we run this refrigerator 24/7, so we are going to provide compressor power, net power, W dot. And then there is a cycle, refrigeration cycle. So there is condenser, which is a heat exchanger. There is a throttling valve, and there is evaporator, which is also a type of heat exchanger. Then this one goes back to the compressor. Oh, I'm not good at painting, but you see, what I'm doing, right? So this is what happens. So we have two thermodynamic devices. The first one is compressor. Did we study compressor? Yes, in chapter 4. And what it is? It's a condenser, and that is a type of heat exchanger. Did we study this heat exchanger? Yes, in chapter 4. And what is this one? It is called expansion valve in refrigeration system. It is a type of throttling valve. Did we study the throttling valve in chapter 4? Yes. And we have another one that is called evaporator. It's a type of heat exchanger. So we have another heat exchanger. So let's see, how it works. We want to, transfer heat from 3 degrees Celsius to the refrigerant. And whatever flows inside is going to be a type of refrigerant. One of the examples that you studied is going to be R134A. Do you remember this, right? That is a type of refrigerant that flows inside. There are many, many different refrigerants. R12, R22, R134A, R blah, 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 blah. There are many, many of them. Then, if we want to observe heat from the food, that refrigerant flowing here should be at lower temperature than 3, right? Then let's assume that the temperature at the inlet, by the way, the direction of this, the refrigerant cycle is this way. Okay, counterclockwise. Then at the inlet of this evaporator, let's say it is 120 kilopascal and minus 25 degrees Celsius. I'm just making up these numbers based on the textbook. Here we have a refrigeration cycle down here. So at the inlet of the evaporator, the refrigerant is at 120 kilopascal minus 25 degrees Celsius. So the refrigerant is at very low temperature. So what's going to happen? There is a heat transfer from 3 to minus 25. Make sense? Yes. So there's a heat transfer from minus 3 to the refrigerant. And this is from low temperature. So I'm going to say Q dot F. Then, because of this heat transfer, what's going to happen to the refrigerant? Its temperature goes up from minus 25, going to go up by 5 degrees. So let's say minus 20 at the exit of this evaporator. And pressure remains constant, 120 kilopascal. And now, this refrigerant just received heat from the milk, apple, and steak. Now we need to transfer heat to the outside. However, outside is 20. The refrigerant is minus 20. Is it possible to have a heat transfer from minus 20 to 20? No. So what we are going to do? We are going to run this compressor. So we are going to increase the pressure of this refrigerant from from 120 kilopascal to 800 kilopascal. That's what a compressor does. Compressor increases pressure. So when pressure of this refrigerant goes up to 800, what happened to its temperature? It goes up too. So from minus 20, it goes up to 660 degrees Celsius. Now the temperature is greater than outside. Can we have a heat transfer? Yes, from here to the outside. This is from the refrigerant system to high temperature. So I'm going to say this is QH, Q.H. Because of this heat transfer, the temperature goes down from 60 down to 30. So we have 800 kilopascal and 30 degrees Celsius. Now we have a throttling valve. What throttling valve does? It drops pressure from 800 kilopascal down to 120 kilopascal. When pressure drops, what happened to its temperature? It drops too. So from 30 to minus 25. So we can keep changing the pressures so we can increase the temperature and decrease the temperature to have a natural heat transfer from low temperature and from to high temperature. That is a refrigeration system. Sometimes, you know, when you power on your refrigerator, sometimes you hear a sound like wee or something, right? That is the sound of this compressor. When the temperature inside the refrigerator goes to higher than a threshold temperature, you may set a temperature 3 degrees Celsius or 3.5 or 4. When the temperature inside, the heat the temperature, that's when this one runs. And we have a refrigerant cycle works to drop the temperature. And this condenser is located usually on the back of the refrigerator. So when you go home, touch the back of the refrigerator, you may feel that it is hot because there is a heat exchanger embedded. If you remember, like a refrigerator a long time ago, 20 years ago or 15 years ago, usually in the back of the old refrigerator, we have a small black pipes, right? When you touch it, it was hot. That was heat exchanger. Nowadays, we don't like that, so we embed under the surface, so we don't see them. But we still, feel the heat from the refrigerator. So that's how refrigeration system works. Okay? Any question? It's pretty simple. Then how many energy transfers? 3. QL, QH, and W net. So we can say this is a refrigeration system, a refrigeration cycle R, and if you move this one this way, we have this refrigeration system R that has 2 thermal energy reservoirs. One is at high temperature, TH. The other one is at low temperature, 3 degrees Celsius, TL. And the direction of heat transfer from low temperature to high temperature, this way, for the amount of Q.L, this way, for the amount of Q.H. And to make that happen, what we need to do? We need to run this compressor. So we have W.net did not, was not produced, was consumed by the refrigeration system. So this is a refrigeration system. Then, how can we analyze this refrigeration system? We can first think about energy balance. What is energy balance? whatever energy transfer goes into this refrigerator should be the same as energy transfer out of the refrigerator. So what goes in? 1, 2. So Q dot L and W dot net, these two are go in. And only one comes out, Q dot H. So let's move to the other side. Then what we get? W dot net is the same as Q dot H minus Q dot L. Don't you think that this one looks familiar? This is exactly the same energy balance equation from heat engine. Then how can we determine the performance of the system? We use efficiency, desired output over required input. So we use efficiency, desired output over required input. So what is desired output? Why do we run this refrigeration system? To consume electricity? To heat kitchen air? No, to absorb heat from the refrigerated space. So what is the heat transfer? Q dot L is our desired output. So we want this to happen, Q dot L. Then to run a refrigerator, what we need to provide? Kitchen air, electricity. So the work, W dot net is required input. By the way, the W dot net is going to be Q dot H minus Q dot L. So we can also say this one is Q dot L over Q dot H minus Q dot L. So that's how you determine the efficiency. Oh, wait. We studied the efficiency from heat engine. What was the equation? The efficiency equation was W dot net over Q dot H. W dot net over Q dot H. No. So if we say this one is efficiency, we got confused between these two. So let's put another name. That is coefficient of performance, COP, of refrigerator. That's how we evaluate the performance of this refrigerator. Some books like to say beta. Beta, COP, they're the same thing. So when you buy a refrigerator, if you're majoring business economy, you can look at the price tag. But if you study science and then if you study thermodynamics, you need to look at what is the COP of the refrigerator. The higher COP, the better the efficiency, right? So that's everything about refrigeration system. Any question? Any question? Is it too hard? So basically what you need to understand is when we have a refrigeration system, it has two thermal energy reservoirs, meaning is that the one thermal energy reservoir is the refrigerated space. We want to remove heat, but we want to maintain a constant temperature. When you run a refrigerator, you don't want the ice formed in the refrigerator. You want to maintain a constant temperature. So whatever inside the refrigerator can be assumed as a thermal energy reservoir. That's a low temperature. And when you run a refrigerator, that heat from the food is going to be released to the outside. But we do not want to, to have a kitchen that is at 40 degrees Celsius or 50 degrees Celsius. We want to maintain a constant temperature inside the kitchen, right? So that let's assume that that's 20 degrees Celsius. Then kitchen air is going to be the other thermal energy reservoir. So you have two thermal energy reservoirs One is at low temperature, which is the inside, and the other one is high temperature, which is the kitchen. By running this refrigerator, meaning is that by consuming power, we can transfer heat from low temperature to high temperature. That's what this cycle is about. Then whenever we have a cycle, then why do we need to understand this, how this one works? Because we want to come up with this equation, COP. By analyzing this refrigerant system, now we know what is desired output, what is required input, so we can come up with this equation. That's it. So that's the governing equation that we are going to use whenever we have a refrigerant system. Okay? Any other question? Then what you need to do, what you need to be to prepare for the exam. It's simple. Whenever you have a cycle, you should be able to determine whether it is heat engine, refrigeration, or heat pump, which is pretty simple, right? Once you are able to determine what it is, you should be able to come up with this schematic diagram, and then you should come up with this how you evaluate the performance of the system, either by efficiency heat engine or COP refrigerator. And one last thing is going to be the energy balance equation. That's all. That's all you need to do. Okay. Now, much more clear now, right? Then, what is the last cycle? Heat pump. I told you that refrigeration cycle is the same as heat pump cycle. So there's no additional theory. Let's look at the refrigeration system one more time. So we have two thermal energy reservoirs. One is where we cool, and the other is where we heat, right? So we transfer heat from low temperature to high temperature, right? That's how refrigeration system works, right? We want to observe heat from low temperature and transfer this heat to high temperature. That's how a refrigerator works. Now let's use this to heat your house. How can we do that? We are transferring heat from low temperature to high temperature. So if you put your house right here, this refrigerator can heat the house. Make sense? Sounds too funny, but that's how heat pump works. So heat pump works in this way. So this side is going to be house, let's say indoor. And this side is going to be what? The other side of the house, outdoor. So we cool outdoor in winter by running a refrigerator, putting the refrigerator outside. Then when you cool this, the outside, what does it mean? We take heat from outside. Once you take heat from outside, you cannot just keep it. You need to throw it away. To where? To inside. So if you buy a refrigerator, open the door, put the refrigerator outside. So you open the door and then locate your refrigerator facing outside. So you're cooling outside the whole way, you're heating inside. Because when you run a refrigerator, that means that you observe heat from the food. The food is going to be the whole way, and put that heat to outside, which is indoor. That is a heat pump. Maybe you can say, okay, that works, but it costs a lot. Because if you want to, put a house on this refrigerator, how big this refrigerator should be. It's going to be pretty big, right? So to run that, the giant refrigerator, isn't it, too expensive? That could be your question, right? So when you talk about, how expensive it is, the easiest way to understand whether it is expensive or cheap is, the compare with, the reference. What is the reference? What is other, the device to heat your house if you don't have a refrigerator? Conventional heater. So let's compare this one with a conventional heater. So you can go to Walmart. Walmart. Is it Walmart sign, right? Yellow, blue, right? No. So you buy a conventional heater. And it says 20 kilowatt. The rating of this conventional heater is 20 kilowatt. So what does it mean? If you consume 20 kilowatt of electricity by this heater, how much heat you can, dump into the house? You spend 20 kilowatt of electricity and then you produce 30 kilowatt of heat? No, that doesn't make sense. Energy cannot be created or destroyed. If you consume 20 kilowatt, you can deliver only 20 kilowatt of heat. So if you consume 20 kilowatt of electricity, the amount of heat goes into the house, so there's a house, is going to be 20 kilowatt. So what is the efficiency? 100%. Any heater that you buy from a Walmart should be at 100% efficiency. So when he says, oh, this one is pretty efficient, yeah, you're right. But everything has the same efficiency because you are converting very expensive energy into a waste energy. How easy it is, right? Anyway, so if you consume 20 kilowatt, you deliver 20 kilowatt of heat transfer into the house. So, okay, that's how, the traditional heater works. So let's consume 20 kilowatt of electricity by this refrigerator. Then what this one does, it's going to cool outside. It's going to, the cool outside air. In other words, that means heat transfer from outside to the refrigerator can be any number. So let's assume that, that we can transfer heat maybe 10 kilowatt. Then how much heat we can deliver to the house? 10? What happened to this one? Can you destroy this one? No. The amount of heat goes into the house is going to be 10 plus 20, 30 kilowatt. So you only consume 20 kilowatt of electricity, but the rate of heat transfer goes to the house is going to be 30. Now, if you compare this refrigerator and conventional heater, which one is more efficient? This one. Then the next question you may have, then why don't we have a heat pump in every single house in Mount Pleasant? How much is it? Or depending on the size, let's assume that the price tag for this conventional heater is $200. Let's assume that $200 heater can heat the house, right? Small house. How much is it? $10,000 or $5,000, depending on the size of the house. So that one is more efficient. But look at the, how expensive it is. The capital cost is very high. That's why, the many houses in here, even though we heat a lot in winter, we don't use heat pump because the capital cost is very high. In other words, you need to buy a giant refrigerator that can cover your entire house, not just milk or apple. You need to put your house here. That's why it is so expensive. Okay? So what you learn is, refrigerator cannot only be used to cool, your food. You can also use it to heat your house. So it's just the way, how you rotate your system, right? Now, so you have a pretty good idea about, how heat pump works. You actually, put your refrigerator in the window or, your door and, the other way, so that it can cool outside, it can, the dump heat inside. Then let me ask a question. Before I joined this university, I was at the University of Texas. I worked there for 7 years. Now here, I'm working for 6 years. So I had a house in Texas and here. Which one makes more sense, to buy a heat pump for my house in Texas or for my house in Michigan? Or are they the same? So there are 3 choices, multiple choice, the question. So buying a heat pump in Texas, buying a heat pump in Michigan, and oh no. So if I, decide to buy a heat pump, which one makes more sense, to buy one for Michigan house or buy one for Texas house? And there is no difference between these two. So number one is going to be, the buying a heat pump in Texas makes much more sense. No one? Okay. Then the buying a heat pump in Michigan makes much more sense. One. So the other is going to be, and there's no difference. Okay, the answer is buying a heat pump in Texas makes much more sense. That's interesting. Why is that? So what is the technology that has been used to heat the house? So we cool outside so that, that heat can go inside, right? So think about this way. Which one is easier to, to cool? Winter in Texas, winter in Michigan. Winter in Texas could be easier to cool because their temperatures are higher. Average temperature in Texas winter could be higher than average, the temperature in Michigan. So cooling warm weather is easier than cooling low temperature. So maybe in Texas, you spend 20 kilowatt, you observe 20 kilowatt and dump 20 to 40 kilowatt. But in Michigan, you spend 20 kilowatt, only observe 5 kilowatt. So the amount of the heat dump here is going to be only 25. What? The price? Yeah. So if you buy the heat pump in Texas, cooling outside is much easier because Texas is warmer than here. So you can dump more heat into the house by spending the same electricity. But in Michigan, outside is extremely low temperature. So cooling that low temperature is extremely hard. So you're spending the same amount of electricity. The actual heat that you can transfer from outside to inside is going to be small. Okay. So if you buy a heat pump here, it's not just one heat pump. It has an auxiliary heater embedded. So heat pump has two options. Run the heat pump and run traditional heater. So the way it works is that you set a threshold temperature. So let's say the threshold temperature is 5 degrees Celsius. So if outside temperature is above 5 degrees Celsius, like the winter in Texas, run the heat pump. If the temperature go below this, then heat pump is not that efficient. So run conventional heater. That's how it works. Okay? Make sense? All right. So that's all theory in chapter 5. So we have 3 problems to solve together. But we won't do that because we are almost, the running out of time. So we will solve these problems later, next week. And just for your information, there's no class this Thursday because I will be out of town. So see you on Tuesday. Okay?